Good morning, chemistry students. Today's video lesson, we are actually looking at standard 2G, where we're looking at models to illustrate the absorption or release of energy. We have seen this before with a physical process. Today, we're looking at it in terms of a chemical process and in terms of chemical reactions. So some things to remember from Unit 1, our indicators of chemical changes. These were the things that we looked for to determine if a process was a chemical change or a physical change. So there are several indicators that we can look for, one of which is a change in color. We saw this with our demo that was done a week or so ago, where I mixed two clear solutions and we got a milky solution. You can see this in your everyday life in terms of like fruit changing colors as it ripens. A second indicator is the formation of a gas. So if we mix two things together and we see bubbles forming, that is a good indicator that it's a chemical change. The formation of a precipitate. So my example for changing color also happens to be a precipitate. It's when a solid falls out of a solution. Frequently in the terms of a lab, formation of a precipitate just makes the solution look cloudy until you actually filter it and separate the solid particles from the liquid. Now we saw how we could use our solubility rules to actually predict what the precipitate in a reaction would be. In terms of acid-base reaction, we could produce water. That is an indicator that it's a chemical change. There are other reactions that will produce water as a product, but that is one where it's highly common. And last but definitely not least, a change in energy or a change in temperature without the addition of a heat source or without it being placed in some type of cooling device. So we've seen this terminology before. We know endothermic reactions or endothermic processes are things that absorb energy, and we know that exothermic processes are things that release energy. But in terms of what does it look like with a chemical reaction, we can actually see it in terms of a plot of the energy versus time. You guys would help if I actually turn my little thingy on. Crap sauce. So looking at that graph, notice on the y-axis, we have energy. That energy, we can see that our reactants are at a higher energy place than the products. Not what I wanted to click. There we go. So my reactants are at a higher energy than the products. All of our reactions will have this type of a hump on them because it does take a little bit of energy being put in to break the bonds to actually start that particular process. This transition state, we're somewhere in between the reactants and the products. But the main thing I want you to notice is the relationship between the height of the reactants and the products. Notice how the products are at a lower energy. They have less potential energy than the reactants. That means that particular process released energy as it occurs. That is known as an exothermic process. It releases energy to the surroundings. If we are doing this in a laboratory setting, you could notice it because the container that the reaction is occurring in actually starts to get warm. It feels hot because the reaction inside is releasing energy. You could also see it in terms of it giving off light, so it starts to glow, or it actually, catches on fire. Now, the thing about our energy in terms of a chemical reaction, that energy is going to be on the product side. Energy is produced. And sometimes we see this as a delta H. So they would actually give us a change in enthalpy. That's what delta H means. Enthalpy is just a fancy word for heat. So it's a change in heat, a change in energy. And when we're losing energy, it is always negative. So we would see a negative delta H value. As indicated with the graph, our products are going to have less energy than our reactants, or the reactants have more energy than the products. You can kind of say it either way. So real world example could be lighting a match. We have to put that little initial strike of energy into it. That would be kind of going up the hill. But once the reaction starts, it gives off heat, it gives off light, and that reaction keeps consuming the match until it's completely used up. That would be an exothermic process. In terms of an actual chemical reaction, notice I have this particular reaction here. It is a combustion of methane, and we can see that that delta H value is negative. So that's telling me that this thing releases that many kilojoules of energy per mole of reaction. Instead of seeing it as a delta H, we can actually see it as a product. That energy is written as a product. So notice when it's in that product side, it's being added as a product. It is something that is produced in combination with the carbon dioxide in the water. So endothermic processes are the exact opposite. Again, we could see a graph of the particular process. Notice my reactants are at a lower energy state than the products. We still have that transition state, but overall, it takes more energy to make the products than we released, breaking the bonds of the reactants. So it had to require an input of energy in order for that reaction to occur. Now, that energy could come from any source. Typically, it could come from like a hot plate or a Bunsen burner in a laboratory setting, but it could just come from the air around the container. So if you have an endothermic process, you'll notice that the container itself starts to feel cold to you because it's absorbing the energy from outside the container. It's absorbing the energy from your hand. If you've ever used an instant ice pack, that would be an endothermic chemical process going on inside. Another endothermic process that you might be familiar with from biology is photosynthesis. Photosynthesis, it requires the energy from the sun. The plant is absorbing that energy in order to produce the products of oxygen and do all the nice fun stuff that the plants do. Now, since energy is added in this process, it is actually shown on a reactant side, or can be shown on the reactant side in the equation, and the delta H is positive. So if it's shown as a change in enthalpy, it is a positive value. That positive value indicates the addition of energy. And I can't spell ADDITION. There you go. Now, the main thing is that our reactants have less energy than the products. Products have more energy than the reactants because we've added that energy in. So as I said, you could see it in terms of the delta H. Pardon me. Value, or you can actually see it as a reactant. It is on the left side of the arrow. Doesn't matter where on the left side of the arrow, it is just showing on that reactant side, indicating that there was an input of energy. So take a moment, pause the video, and see if you can identify each of these descriptions as being endothermic, exothermic, and then come back and see how you did. So looking at our first example, if our products have a higher energy, so maybe that visual aid would help you. We have our reactants indicated with an R. My products are at that higher energy state. That means it must be an endothermic process. If the process releases energy, by definition, it is exothermic when it releases that energy. For C, notice that the energy is on the right side of the arrow. And since it's on the right side of the arrow, that is also an exothermic process. For D, we're showing a delta H value. And if that delta H is positive, it means we input energy. So if we input energy, it is an endothermic chemical reaction. For E, if it requires less energy to break the bonds than released when forming the bonds, it requires less energy to break the bonds than released when forming the bonds. That means my products are higher than my reactants. So, I mean, yeah, I would have that little hump in there, but we are looking at an exothermic process. For F, if we are absorbing energy, the absorption of energy by definition is an endothermic process. And for G, if my reactants have a higher energy than my products, my reactants are at a higher energy than my products. We can see that products lost energy, therefore it is exothermic. In terms of my reactions, that negative delta H is indicating that it is an exothermic process. We released energy, we gave away energy. That's why we use that negative sign. For J, notice my arrow here in the center, and that energy is on the reactant side. It's on the left side, therefore it must be endothermic. And last but definitely not least, we have the fact that it takes more energy to break the bonds than released when forming the bonds. It takes more energy to break the bonds. That means we have to put in more energy. Therefore, it is endothermic. You do have some endothermic, exothermic practice in Google Classroom. And of course, I'm available if you have some clarifying questions that you need assistance with. As always, have a wonderful day, and hopefully this video does not glitch again.